Hi, I'm Cameron, and I'm the product lead for the Go programming language at Google.
And I'm Marc. I lead developer relations for Go.
For those of you who are new to our project, Go is an open source programming language supported by Google that enables developers and software engineering teams to quickly build more secure, reliable, and scalable production systems. Google released Go as an open source project over 15 years ago, after starting it 2 years earlier in response to Google's own challenges with building and maintaining large-scale, mission-critical systems. With existing tools, we had to choose between the productivity of dynamic, interpreted languages and the production readiness of strongly typed, compiled languages. But we wanted both, so we built Go. Go's core premise is that developer tools should prioritize scale from the start, which means accounting for how modern software is architected, the environments in which modern workloads run, and, most importantly, the teams that write, operate, and maintain it all. So with that in mind, we framed Go around 3 principles that continue to guide us to this day. First, Go is productive. It's simple to learn, simple to maintain, readable, and scales well across teams, workloads, and use cases. Second, Go is more than a language. It's a complete developer experience. From the IDE to production, we provide end-to-end solutions with touchpoints all across the software development lifecycle. And we provide all of it out of the box with sensible, self-tuning defaults. And third, Go is production ready. It's reliable, efficient, stable, and secure, which makes it well suited for everything from simple apps to enterprise systems and critical infrastructure. Over the years, Go has found itself at the center of the modern cloud, and by extension, the modern web. Many of the world's best-known cloud technologies are written in Go, including Kubernetes, Docker, Terraform, and more. And companies large and small, from individuals to startups to enterprises, have all embraced Go, especially for their cloud-based workloads. And that's in large part because Go was purpose-built for the cloud. The libraries and integrations and architectures that Go enable were meant for the cloud, not retrofitted for it later, which means you can realize the cloud's benefits faster and easier than you can in other languages. But you don't have to take my word for it. Go users consistently give us extraordinary feedback and customer satisfaction, levels that are practically unheard of in the industry. And the usage shows it too. Today, Go is more popular than ever, with millions of developers and growing fast. In fact, according to a new Stack survey from last year, Go is one of only 2 languages growing faster than the developer population itself. The other one's Rust, which we think pairs really well with Go, but that's a talk for another day. And there are signs like this everywhere you look. Go consistently ranks among the most loved technologies on Stack Overflow. And last year, Cloudflare reported that Go is the #1 language powering API calls on the internet. So whether you're an individual developer, an enterprise, or something in between, Go enables you to build and scale up your projects quickly and more reliably. And you'll probably be happy you did. Next, Marc will dig into all the latest in Go. Off to you, Marc.
Thanks, Cameron. Go releases new major versions twice a year, in August and February. In the last year, we released a lot of exciting new features in 1.23 and 1.24 to help you and your team be more productive. In 1.23, we introduced iterators with the seek and seek2 types. In classic Go fashion, iterators are more than just a new type in the standard library. They're an elegant way to simplify loops using the already familiar for range expression and keeping the mechanics of iterating separate from the body of your loop. Before iterators, there were a couple of different ways to loop over data. Some methods would return a slice containing all the results, which can be inefficient for large collections. Another way was to create your own iterator object like this code, which uses the Google Cloud Storage Library. Notice the complexity here? We have flow control and error checking in our loop, and that error checking needs to be duplicated in every loop. With iterators, you can use the familiar for range syntax to perform the loop, and the complex flow control is kept inside the iterator. This lets our loop body stay focused on the handling of our files or our errors without worrying about flow control. The standard library, as of 1.24, includes a bunch of iterators in the strings, slices, and maps packages. Because iterators are just a function, you can define your own, including for collection types defined elsewhere. Here's the iterator I defined for the cloud storage example. The declaration looks a bit complex, but you can see our flow control here has the same effect as before. This iterator lets us factor out the flow control handling from our loop and make them more readable. As new concepts like iterators are introduced, Go's vertically integrated tools help keep your codebase up to date with the latest patterns and idioms. Go's language server, GoPlease, can integrate with your IDE, either with the language server support found in most IDEs or through a plugin like the VS Code Go extension. GoPlease helps with the usual language server things like type checking, function signatures, and references, but GoPlease can do so much more. Remember that complex iterator definition? Since GoPlease knows about new features on day one, it can help you avoid mistakes while you're writing them. Here, it's noticed an error where our iterator may call our yield function after it should have stopped. GoPlease includes a suite of modernizations, common patterns that have since been addressed as language features or standard library additions. And while you could run the modernizer over your whole codebase, GoPlease can suggest them inline wherever you're editing. Here, we have some examples of older patterns on the left and their modernized replacements on the right. That last modernizer showcases a new feature of the JSON parser called omit0. The JSON package has been a part of Go since 1.0. It enables ergonomic development of API clients and servers by simplifying serialization of Go structs. The addition of the omit0 option resolves some common errors and surprising behavior when dealing with Go's zero values, like empty structs and uninitialized time.time objects. These additions give you more control over how your objects are serialized to JSON and avoid possible sources of error and confusion. Do you need to update your Go runtime to take advantage of a new feature? As of 1.23, you can use Go-Get to manage the Go toolchain just like any other dependency. Go will download updated toolchains as needed, allowing your teams to use the latest features without stopping to update their toolchain manually. And this applies to dependencies too. If you take a dependency on code that requires 1.24, Go will update your module's Go directive to require 1.24 and automatically fetch the 1.24 runtime. The Go language and the Go tools continue to find new ways to help you keep your codebase readable and modern and allow your team to stay focused and productive.
Marc just walked you through some of the new features that make you more productive. But remember, Go is about productivity and production readiness. So let's talk about the latest features from Go 123 and 124 that make your applications more robust, more secure, and more performant. As I said earlier, Go's founding principles center in part on its portability and a focus on the modern environments in which modern workloads run. These environments continue to evolve, and as they do, we want to be sure that Go keeps up. One way we've done that is by significantly improving Go support for WebAssembly in Go 124. WebAssembly, or WASM, is a binary instruction format and sandbox runtime environment that unlocks a lot of new interesting use cases, especially on the cloud. Several languages, including Go, are capable of compiling WASM modules that contain portable, architecture-agnostic bytecode that runs on all WASM hosts. The same WASM host application can call methods from multiple different WASM modules, which can be written in one language or a mix of languages, as appropriate. These WASM modules are hot-loadable and run in a memory-safe sandbox runtime with structured control flows and verification. Any system calls are routed through the WASM runtime, which provides an extra layer of security, something like an extremely lightweight container. And, despite this layer of abstraction, WASM applications are exceptionally efficient, capable of achieving near-native performance on their hosts. This makes them particularly useful for high-performance, low-latency use cases, like computing at the edge. For example, you can run your WASM code on Google Cloud Service Extensions, which provides edge computing at over 200 edge locations across more than 200 countries. Go first introduced support for WASM in Go 1.11 with the JS WASM port. WASM itself was originally designed for browsers, and the JS WASM port enabled this use case by allowing you to target web pages through a JavaScript host. Go developers made some really fun stuff with this capability, especially games. There are even open source game engines for Go that leverage the JS WASM port. Go developers can use these projects to easily develop impressive 2D games that run in the browser. As WASM evolved, Go did too. In Go 121, we introduced support for Preview 1 of the WebAssembly System Interface, or WASI. WASI provides a POSIX-style interface for interacting with system resources, like the file system, system clock, data utilities, and more. In this example, you can see a simple Hello World program that we compile the WASM via the leading compile flags. We can then run the program using one of the many free open-source WASM runtimes and libraries. In this case, we're using WASIRO, an open-source project implemented in Go. Starting in Go 121, Go developers could build a WASM module as an executable, start it in a WASM runtime, and run it to completion. And that brings us to today. In Go 124, we expanded Go's WASM capabilities in two big ways. First, Go 124 enables you to export Go functions to the WASM host with the Go WASM Export Compiler directive. When we compile code like this into a WASM module, we can import it in a WASM host, and the WASM host can directly call the module's exported functions. Second, Go 124 added support for building WASI reactors. When you use this capability to build a WASM module in reactor mode, the module can remain initialized even after it is finished executing. This is really useful for long-running plugins or extensions that you want available indefinitely. Initialize it once, leave it running, and it can continue to respond to calls, including by maintaining state. In this example, we use libraries from WASIRO to create a WASM host that will call the add function we exported in the previous example. This time, though, we'll build the WASM module in reactor mode with the highlighted build flag. Now we can run the add function more than once without reinitializing it. Next, let's talk about how Go makes your applications more secure. Go has always led in security features and capabilities. In Go 113, we introduced the module proxy and checksum database, which cache and record hashes for all dependencies in the Go ecosystem, protecting you against man-in-the-middle attacks and other tampering of your dependencies. Then, in Go 118, we introduced built-in fuzz testing, the first major programming language with native fuzz testing built into and integrated with its standard toolchain. You can think of fuzzing as a form of automated testing that intelligently manipulates inputs to your program to flesh out bugs, especially security vulnerabilities. And in 2022, we introduced Go's end-to-end vulnerability management system, which surfaces known vulnerabilities in your dependencies everywhere from your IDE to the runtime. By analyzing the call graph from your code through your dependencies, Go's vulnerability management tools are able to detect whether you actually invoke vulnerable code, eliminating the vast majority of false positives. Building on our security focus, in Go 124, we introduced support for post-quantum cryptography, all of it implemented transparently behind the scenes. We also improved support for FIPS 140, a U.S. government compliance regime that includes approved algorithms for cryptographic applications. You can enable FIPS mode without any changes to your code, either at runtime with the highlighted debug flag or at build time with the highlighted build flag. Finally, we've continued to focus on making Go faster and more efficient. One important way we've done this is through the introduction of a completely new implementation of the built-in map type, based on a new hash table design called Swiss tables. Beginning in Go 124, maps transparently use the new Swiss table implementation. In micro benchmarks, map operations using the new implementation are up to 60% faster than they were in Go 123, especially for large maps. And it's all seamlessly integrated in Go's built-in map. No need to adjust your code, just upgrade and you're set. And there's more, including lots of new low-level tools across both Go 123 and 124 for efficiency. For example, in Go 123, we introduced the unique package, enabling the efficient deduplication and comparison of values. In Go 124, we introduced weak pointers, which enable you to safely point to an object without preventing it from being garbage collected, as well as the add cleanup function, a finalization mechanism that is more flexible, more efficient, and less error-prone. And there's more, including improved memory allocation speeds and general speed improvements throughout. And all of it continues our focus on keeping Go both productive and production ready. Next, let's turn it back to Marc for a quick rundown on the latest in Go's use in generative AI.
As you've just heard, Go is packed with features that make it a great language for production systems. Features like efficient networking libraries and integrated struct tags make it great for building distributed systems. And that's a big part of why Go is so prevalent in cloud infrastructure and services. And those same reasons are why Go is a great choice for building AI infrastructure and services today. Popular generative AI tools and libraries like Ollama, Local AI, LangChain Go, GenKit, and many others are all written in Go. Like the major infrastructure projects before them, these tools and libraries leverage Go's productivity and production readiness to create highly scalable and more reliable mission-critical services that millions of developers from various language ecosystems rely upon for their AI-powered workloads. In fact, cloud and AI systems have more in common than you might think. Since LLMs often require dedicated, specialized compute resources, they're usually run as a network service called through an API. Let's consider the example of a retrieval-augmented generation system as outlined in a recent post on the Go blog. Our RAG system uses a vector database to store relevant documents to feed to our LLM when answering the user's questions. Vector databases rely on a specialized embedding model so we can efficiently query for documents that are similar to the user's question. We'll look at 3 different frameworks we can use to connect these services together. For our first example, we'll use the Gemini and Weaviate client libraries directly. This code comes from the user query handler. We're using Weaviate's GraphQL interface to fetch documents, and the query itself is a bit long, so we use the helper function. One downside to this approach is that we'd have to rewrite our helper if we change our vector database. Here, we're using LangChain Go, which provides interface abstractions for our LLM and vector database. The similarity search and generate from single prompt calls won't need to change if we replace those components. Last, we'll look at Firebase GenKit for Go, currently in beta. It provides similar abstractions to LangChain Go. GenKit includes production-grade features like prompt management and observability that may not be visible in the code, but improve the overall developer experience. As your AI systems grow, Go's emphasis on simplicity means your code remains readable even as it grows in size and complexity. Go features like object embedding and interfaces allow for seamless migrations as requirements and technology change, and they always change. Go's proven ability to keep up with rapid change has made it successful in some of the best-known components of cloud infrastructure. The same features that drove Go adoption in cloud make it an excellent choice as we build the AI infrastructure of tomorrow.
As I hope we've demonstrated in this video, Go's founding principles around productivity, developer experience, and production readiness are still how we prioritize our work today. Before we conclude, I want to take a few minutes to give you a peek at what's around the corner in Go 125 and beyond. First, and building on Marc's discussion around AI, we're very excited about work we're doing around SIMD. SIMD enables modern CPUs to perform vectorized array manipulations, running certain kinds of loops in parallel. These capabilities are essential for many kinds of performance optimizations, including the sort required for certain kinds of AI infrastructure. Rounding out our performance work, we have a lot of exciting opportunities around multi-core hardware, including garbage collector and scheduler capabilities that make better use of non-uniform memory access in modern CPU architectures. Switching to the language itself, we have a lot of polish ahead of us in our continuing push to improve productivity, especially around flexibility in generic operations. For more information on that work, check out our discussions on the Go project on GitHub. And as we do all this, and more, you can rest assured that any changes we make now and in the future will continue to fulfill the Go promise of compatibility. Go remains, and will always remain, fully backward compatible to Go 1.0. As we wrap up, we want to take a moment to thank the Go community. We, the Go team, are committed to keeping Go productive and production ready, well into the future. But we know we aren't alone. Today, our ecosystem is larger and more robust than ever, and we continue to see a lot of really high-quality tools and libraries emerge, especially for new use cases around generative AI. and we see hundreds of thousands of Gophers around the world meeting up, attending Go conferences, and collaborating online, all because they love Go. So thank you to the Go community. It's because of your contributions that Go is growing and more relevant than ever before. We're very proud to be a part of this journey with you. To get started, or for more information on anything we discussed in this video, be sure to check out our homepage at go.dev. Thank you for joining us this year at Google I/O. We can't wait to see what you build with Go this year and in the years to come.